All right, so I wanted to talk about a ball or an object thrown downwards. Okay, and in that case, the motion map would look something like this, right? You have a beginning velocity, so my first velocity vector is not a dot, and these would be my velocity vectors, and they'd be changing over time. My acceleration would be constant, unchanging over time. So these are my acceleration vectors. Now I've got position. I'm using y because this is in the downward direction. I'm going to choose to make down positive. Okay, and then I got velocity in the y direction. I think I forgot that those symbols on the last one. And then I got acceleration in the y direction. Okay, and then I got my net force versus time graph. So both of these should be positive values, right? And my velocity graph should look like this, and my position graph should look like that, right? And I'm going to start with the simplest one, this area here, right? That's going to be, let's see, change in velocity, right? Which is a vector, which is my final velocity minus my initial velocity, which are vectors, which is acceleration times time. Acceleration is a vector, right? And let's see here, these vectors, well, my acceleration's down, right? So that means my change in velocity vector is down. So my acceleration time vector, if it looks like that, if that's its length, then my change in velocity vector would be identical. Now, if you're going down and you want to subtract vectors, right? Your final vector is down, your beginning vector is down, but I have to reverse the direction of my initial velocity, right? So I have to draw, my final velocity is longer, right? So my final velocity is down, but now I have to subtract or add the negative of my beginning velocity. Might look something like that, right? So this gives me a sense of how these vectors are related to one another. So my final velocity, if I superimpose these vectors here, right, this would probably be useful. This is my AT vector, or it can be my change in velocity vector. Either way, it's correct. So I really have two ways I could write this. Final velocity going down like that. Initial velocity like this. This is my change in velocity. Okay. So those are some vector representations of that graph. Now, if I look at this here, I have a rectangle and a triangle. Well, this part is going to be my beginning velocity in the y direction. That's going to be my final velocity in the y direction. So this is always going to be my change in velocity, which has a magnitude of AT. So what I'm looking at here is 1/2 AT squared, because I have a base that is a length of t. So 1/2 AT squared vector plus v naught in the y direction, t, v naught in the y direction is a vector, but t is not. T is a scalar. So when I add these two vectors, oh, this is a cool one. when I add my 1/2 AT squared vector and my V naught t vector, I should get my displacement vector, right? That is quite cool. And to show those vectors, well, my displacement is down, right? So I'll draw a vector down to show my displacement. My 1/2 AT squared and my V naught t squared, my V naught t vector have to add to this vector. So I'm going to place them head to tail. So my 1/2 AT squared vector, and I don't know which one's longer. I don't care. I'm just representing it in a way that makes sense in terms of the vector addition. So V naught t and 1/2 AT squared, those magnitudes add together to give me my displacement in the y direction. I could also I would probably have my object start at a 0 position just to make things simple. So you could argue that this is also the same, that my displacement vector is exactly equal to my final position vector if you start with a 0 position. Anyway, that's it. You can see things get more complicated, but still quite reasonable when dealing with the vectors. And you can use this approach to solve every problem on that worksheet, and you should probably practice. Anyway, hope you have a good day. Thanks for watching. Hope it helps.